Okay, so I think this, did you turn on? Hello? Okay. All right, thank you. It is a tremendous honor to be here today to talk in this conference celebrating all of the great mathematics of Peter Sarnak. One thing that I find particularly inspiring about Peter's work, which I think we all see reflected in this conference and the speakers and topics of this conference, is the unity of mathematics that you can see through Peter's work, from number theory, analysis, probability, dynamics, topology, and how all questions in all of those areas are better understood by understanding more about other areas. So that, yeah, that for me personally is something that I especially admire and appreciate about Peter's work, and it's been an inspiration to me. All right, so today I'm going to talk about some work on distributions of class groups, and what I talk about today is joint work with Will Sawin. Okay, so, all right, for every number field, every finite extension of Q, there's the associated finite abelian group, the class group that controls the arithmetic and factorization in K. And the very basic question that I am going to be thinking about in this talk is, as K varies in natural families of number fields, and so those are usually of fixed degree in this context, and usually a fixed Galois group. What is the distribution of finite abelian groups, class groups that we see? So this is one of the foundational kind of motivating questions in an area that now people are calling arithmetic statistics. And because class groups control so much else about the number fields, you can often use this to understand other kinds of statistical questions about what's out there in terms of number fields. So in the 1980s, there wasn't the term arithmetic statistics yet, but people were thinking about these questions. So Peter, of course, was thinking about questions about the distributions of the sizes of these groups in families of quadratic fields. And you can think of that as a sort of Archimedean question about the distributions of the groups. And at the same time, Cohen and Lenstra were thinking about a more sort of p-adic question about the distributions of the p-CeLO subgroups and the group structures themselves. And so in 1984, Cohen and Lenstra gave conjectural distributions of class groups, in certain cases based especially on where they had extensive numerical computations, tables of class groups. And partially these distributions were motivated by those tables of class groups, and see, well, when you look in these class groups and you look at, say, the 3 CeLO subgroup, you see a Z mod 9 a lot more often than you see a Z mod 3 cross Z mod 3. Now, maybe you think there's some general obstruction to class groups being too big, but those are the same size group. So what should the difference be? We'll get to their conjectures, but so they made distributions, they gave conjectures for the distributions of the class groups of real quadratic fields and complex quadratic fields. And of course, if you've looked at class numbers of quadratic fields at all, you know that the behavior is quite different depending on the signature of the field there. So, I said natural families, and then as soon as you start looking at tables, you realize that part of what you want to include in natural families is some signature behavior, some behavior about the fields at infinity. And they also gave conjectures for the distributions for any abelian group A for totally real, only the totally real case, totally real abelian A extensions. But later in 1990, Cohen and Martinet extended the conjectures to really give full conjectures for distributions of class groups. So for G extensions, so Galois extensions for an arbitrary finite group G, and of an arbitrary number field. So not just when the base field is Q, but just G extensions. So you fix some number field, you look among all G extensions of that number field, and then you ask about the distributions of class groups you see. And you can essentially, at least in the way that we're going to talk about it today, get the non-Galois case from the Galois closure. So these were reasonably exhaustive conjectures. And the conjectures in particular, just like I mentioned in the quadratic case, they depend, there's a different conjecture depending on the behavior of the infinite place of the real and complex embeddings of K. All right, so I'm going to state a version of their conjectures. So if we have a G extension, one thing to think about is that the class group is not just a finite abelian group. If we have a G extension, then that Galois group G acts on K, and thus it acts on the class group. So what the structure we're really trying to understand is this finite G module, not just an abelian group. And when you think about it as a G module, there is some part that comes from the class group of the base field. So this K naught, this base field we're taking, it has some class group that maps to the class group of K. And that provides some sort of, as you vary over all G extensions of K naught, some sort of fixed part of all of those class groups that you could say is understood in any of these fixed problems where you fix the class group of K naught. And so the part that is varying is this quotient. We're going to call it the zero class group with this upper subscript 0, where we take the quotient by the class group of the base field. And then just some notations. As I said, we're going to have to consider the signature information. I'm going to label some complex conjugations of K, one for each complex embedding, or one from each pair of complex embeddings of the base field. So I'm only picking one complex conjugation over any one of the base field. And so with this notation, the conjecture of Cohen-Lenstra-Martinet is equivalent to the following. So if we take a prime, P, that doesn't divide the order of G, and so if you were worried here at all about this map, or this having taken out the fixed part, and if you had any concerns about that, then you'll see, because we're avoiding primes that divide the order of G, there's nothing tricky in the behavior of the fixed part of the class group. So for any such prime in an abelian P group A with an action of G, since we said the class groups are not just abelian groups with the action of G, where that group has trivial invariance, if we range over G extensions of K naught, the conjectural probability that the CeLO P subgroup of this class group, this reduced class group, so I write P to the infinity torsion here for the CeLO P subgroup, and not just the CeLO P subgroup, but the CeLO P G module here, that's isomorphic to A. So this CeLO P subgroup is some abelian P group with an action of G, and what are they conjecturing the probability that it's A is? So it's some explicit constant that doesn't depend on A. This is a number that you can put in to make sure all of these probabilities sum up to 1, divided by the number of automorphisms of A as a G module. So that's what that subscript G means. So I'm not just taking the automorphisms of A, but as a G module. And then some factors depending on the size of the subgroup of A that's fixed by various complex conjugations. All right, so let's take just a minute to think about some of the things that are happening here. So first of all, one of the big pieces here, and most important pieces, is this factor in the denominator of the size of the automorphism group as a G module. So that is a really central idea in this Cohen-Lenstra-Martinet philosophy. And it's that when you don't know anything about how an object should be distributed, it should be distributed like 1 over the number of automorphisms of the object. But you need to make sure that you take into account what kind of object it is. And so if it's not just an abelian group, but it's a G module, you should take the G module automorphisms. All right, so that's somehow what should draw your attention first. And then this factor, well, even in the case of quadratic extensions, we expected there has to be something that really accounts for the fact that the real quadratic class groups, for example, are much smaller than imaginary quadratic class groups. And so, of course, in the case of for example, totally real field, these complex conjugations will be trivial, and so you'll have a bigger piece of A that is fixed by them than if you have some complex conjugations. So this factor basically, makes your group smaller the more real it is, and that was, that I think was motivated at the time by a combination of data from tables and wanting something that could fit together in one piece. Though Cohen-Lenstra-Martinet didn't actually write this formula down in this way, they wrote something a little more complicated that you can simplify to this. But the idea of those factors, there were some vague philosophies about them, but at the time, I think mostly it was to match the data, which was what was motivating these conjectures in the first place. Okay, so one other thing is, so what is this about trivial invariance? It's because I got rid of the part of the class group that came from the base field. And here, because we're only looking at CeLO P subgroups for P not dividing G, the fixed part of the class group is exactly what we got rid of by getting rid of the class group of the base field. I hope that that makes sense in analogy to the fact that like K0 are exactly the elements that are fixed by G. And so once we get rid of that fixed part, that's not varying, there's no interesting distributional question. Of course, what's left is not just a P group, abelian P group with an action of G, but it's one with trivial invariance. So we have to sort of put on all the conditions that we know. It needs to be a finite abelian P group. It needs to have an action of G. It needs to have trivial invariance. And then after that, this conjectures that everything happens with positive probability. So that's quite a strong thing. I mean, we're very far from knowing something like this, even in the quadratic case. Examples of quadratic fields with even moderately large 3 rank are not to be found yet, and yet Cohen-Lenstra-Martinet conjectured that in fact it's a positive proportion of all quadratic fields to have any particular 3 CeLO subgroup as their class group. Yes.
Maybe I'm missing something. For a G extension, all of the complex embeddings should be transitively mapped to each other by G. All the sigmas should be conjugate in G, and therefore all the A upper sigma i's should have the same order.
Oh, let's see. So I took only one complex conjugation above each one of the base field. And so, yeah. So I took out all those ones that you were thinking were the same in some sense. And I'm I'm talking about the different ones because because K naught doesn't have to be Galois. Good question. Yes. Yes, on the CeLO P subgroup where P doesn't divide G, it is an injection. It is not necessarily at primes that divide G. And we are ignoring today completely the questions of primes that divide the order of G. There's a sort of different kind of story there. All right. Yes, so you definitely need the G action. As I said, you need to say that it should be an invariant-free thing since we got rid of the fixed part in that quotient by K naught. And then, as I said, otherwise the conjecture is that everything occurs, and it occurs with positive probability. All right, and so then sometime later, Günter Malle was creating tables of class groups and looking at them and trying to see, in particular, if these conjectures of Cohen and Lenstra-Martinet were true now. Sometime later, so a little over a decade ago, when there was much better computational power than there was in the 1980s when they first made these conjectures. So Malle gathered extensive computational data on class group distributions, and he found some irregularities. So I put up a table of some of his data. So this prediction in 5, this is the Cohen-Lenstra prediction. You can see these predictions, and these are on a statistic on the P part for P equals 2, 5, 7, 11, 13, 17, as you consider more and more fields. So going down this table, he's considering fields of larger and larger discriminant. P equals 3 is not on here because that's the theorem of Davenport-Heilbronn, so he already knew that one was going to work out. Though it still might have been interesting to compare the convergence rate. And if you look at these tables, most of the columns look quite good. They appear to be converging to the number at the bottom, except this one. This is clearly converging to 1.5, not 1.25. So that, and these are for C3, so cyclic cubic fields. Oh wait, never mind. I lied. I was thinking, yes, sorry. I was thinking that these were degree 3 fields when I said that about Davenport-Heilbronn. That was totally wrong. This was not about Davenport-Heilbronn. I just forgot which chart we were looking at. These are cyclic cubic fields, and P equals 3 is not there because there's a genus theory effect, and it is in part of this other story that I mentioned that we won't be talking about today. Yeah, so these are cyclic cubic fields. And so they're cyclic cubic fields, so the Galois group is just Z mod 3Z. So from that point of view, like there's 2 doesn't have any particular relation to the Galois group, but yet there was something going wrong with the conjectures at P equals 2. And looking at his data, Malle said, okay, well, Cohen and Lenstra conjecture the probability that a cyclic cubic, a C3 extension of the rationals, has class group with 2 rank 2R, and it has to be even. It turns out, so this condition that there should be a C3 action and it should be invariant free means that the dimension has to be even because there's only one non-trivial irreducible representation of C3 mod 2, and it's even dimensional. So the probability that you get some particular 2 rank is, all right, and so here's some formula. So this is what it works out when you take all the 1 over aughts, and this sort of would involve, summing the 1 over aught kind of thing over lots of different groups that have that 2 rank, because of course the 2 rank does not determine even the group structure of the finite abelian 2 group, but you get this formula. The numerator is a constant, and the denominator mainly depends on r through this exponent here, roughly 4 to the r squared, though there are also r's in the bottom 2 factors. And based on his computations, Malle conjectured that it instead should be the following formula, and he came up with this formula by looking at the data. And I think it's right. I mean, it's totally amazing to me, his ability to see this pattern. So as you see, again, the numerator is a constant, but the dependence on r is sort of quite different here, in that it's like 4 to the r squared over 2, and some of the other factors are just slightly different. So from Malle's point of view, he was looking at tables and sort of saying, well, this is the kind of distribution I'm seeing. And of course, he wanted something that had a somewhat nice formula and summed up to 1. And came up with that. And it gives much better agreement with the data. So this is a chart just about some statistics on the 2 ranks and higher moments of 2 ranks for these C3 fields. And this formula 1 here is Malle's prediction, and the last row is the Cohen-Lenstra prediction. And you can see here on each of these statistics, like, he is spot on. Of course, you shouldn't be surprised, because he conjectured the formula, so that would be true. I mean, that was, he came up with a formula so that it would match the data that he had. And you can see some of it is quite, the Cohen-Lenstra prediction starts to get quite far off. All right. Okay. Okay, that was something going wrong with the 2 ranks of cyclic cubic fields. But more generally, in his tables, Malle found empirical discrepancies in the CeLO-P subgroups of class groups whenever the base field had pth roots of unity. So we were talking about CeLO-2 subgroups of class groups of cyclic cubic fields. But CeLO-2 subgroups, of course, the base field has 2 roots of unity, because every number field has the second roots of unity. And so here's like one example. Here, when he looked at quadratic extensions, even just quadratic extensions of Q adjoin the square root of -3, everything looks, all the primes away from 2 and 3 look fine for Cohen and Lenstra's prediction, but the 3 ranks look incorrect, which, I guess, is related here to the fact that this base field has 3rd roots of unity. So here again, this was the original Cohen-Lenstra prediction, and he made some new prediction on the distribution, in this case of quadratic extensions of Q joins zeta 3 that much better match the data. So then in the sort of, ensuing years since 2010, there has been a big understanding that there's something wrong with these Cohen-Lenstra-Martinet heuristics when there are roots of unity in the base field of order P, and you're looking at the CeLO-P, trying to predict the distribution of the CeLO-P subgroups. However, it has not been totally clear exactly how to correct for that, or what the alternative phenomenon is in general. So there have been several papers that have tried to correct for roots of unity, making new conjectures. So as I mentioned, in his original papers looking at the data, Malle gave further conjectures for a few Galois groups, correcting for some roots of unity in the base field. Always in cases where there were pth but not p squared roots of unity. He had some data but couldn't kind of come up with formulas that seemed to match it. When there were, say, fourth roots of unity. And it was only for a few cases of Galois groups, quadratic C3, C5 extensions, but not in any, not even like a general abelian extensions or anything. So just some special cases of Galois groups that he had data for, because he was conjecturing these based on the tables. Later, Adam and Malle gave conjectures for some more special Galois groups whose representation theory had some very special properties, and they allowed any amount of roots of unity. But their conjectures were interesting. They weren't. They didn't conjecture specific formulas. Now it was of a different sort of flavor. They conjectured that the probability should agree with a limit of distributions coming from random matrices. So that gave a sort of more of an idea of of these distributions coming from somewhere, but they didn't prove that, that the limit of distributions from random matrices existed or find what it was. So it's sort of the opposite end of the spectrum. It's kind of a conceptual description of a distribution, but without being able to say what it was explicitly, compared to Malle's earlier paper where it's very explicit. And then in 2020, Lubnowski, Sawin, and Zimmerman gave a rather complete conjecture just for quadratic extensions, but they did give explicit formulas for the distribution with any number of roots of unity in the base field. So not just p, but p squared roots of unity. And so this work that I want to present today that is joint with Will Sawin is for all Galois groups, so addressing this original question for all Galois groups and any amount of roots of unity in the base field, and we're going to give explicit formulas for the conjectural distributions of the CELO P subgroups of this reduced class group for every prime that doesn't divide the order of G. And our conjectures actually come from another motivation, a function field theorem. So in this whole story, I was talking about number fields, finite extensions of Q. You can replace Q with FQT, the field of rational functions over a finite field in this whole story, and talk about function fields over finite fields, finite extensions of those FQTs, and ask all the same kinds of questions. And so work that I did with Yuan Liu and David Zurich-Brown gave the moments of the distribution of these reduced class groups as Q goes to infinity in this function field setting. So one fun thing about the function fields is we think of this function field over finite field as being an analog of Q, but there's not just one rational function field over a finite field. There's one of them for every Q. And so you have this flexibility to let Q go to infinity. And of course, the really powerful thing is that these function fields have another life as curves over finite fields. And so this work that I'm referring to here used the algebraic geometry of moduli spaces of curves over finite fields to find certain statistics, and I'm going to talk more about what I mean by moments in this setting, but there are certain averages over the distributions, and so we found those averages over the distribution as Q goes to infinity in the function field setting, so that is a kind of theorem, something that's very far away from what we're able to do in the number field case here, and so these averages, these moments, what is new in this work that I'm talking about that's joint with Sawin is that we showed in a paper of ours about moments and the moment problem that these moments, these averages, and I'm going to tell you what they are on the next slide, but they determine a unique distribution of G modules that can be given explicitly. So there are two things that happen in this theorem. One is that it said that these averages that had been found using the algebraic geometry of moduli space of curves over finite fields in this earlier work, those averages were actually enough to tell you everything about the distribution. And secondly, not just to tell you it theoretically, like it had to be something, but you don't know what it is. But, and this is important and important in the rest of the story, that from the actual moments, from the averages that we had found, we could work out explicitly what the distribution was. Okay, so our conjecture on the distribution is, so if we take a prime not dividing the order of a finite group and we we fix a base number field that, say, contains the p to the rth roots of unity, but not the p to the r plus 1 roots of unity. So these conjectures depend on exactly sort of what levels of roots of unity you have. So I'm first going to give the sort of the easier to state, but in full generality version of the conjecture. So among G extensions, the distribution of G modules, and I say invariant free, remember that the CLP subgroup of the class group, we're taking this reduced version where we get rid of the fixed part, so it will be invariant free, only has one, the identity is the only invariant element, is the one with these following averages. Okay, and so now this is what I mean by the moments. Okay, so this is expectation. This expectation is in K as we vary over K, and I'm sweeping under the rug exactly how you do that, but imagine that you list all the K and you're sort of going through and you take the first however many of them, first X of them, and let X go to infinity. So as you average over K, the number of surjections, and this surjections has this sub G, so that means as G modules, so surjective homomorphisms of G modules from the CLP subgroup of this reduced class group to B. So this is some fixed B. So these moments that I was talking about before, they were some statistic of the distribution of G modules. And what that statistic is, it's indexed by B, by the G module B. So if you're thinking of distributions of numbers, of course, you usually talk about moments indexed by a natural number K, the kth moment. And so here, these moments are indexed by G modules B. And the bth moment is this average number of surjections as G modules from this random object to the fixed object. And so for each B, there is some average, and we are conjecturing that this is the average. Okay, so this is some quantity that depends on B, and the denominator, you just have the size of B. Here you have the second wedge power of B, and then you take the G invariance of that. Of course, even if G doesn't have invariance, when you do the representation theory, you take the exterior power there, that might have invariance, and we're just taking the size of the P to the R torsion. P to the R came from the roots of unity, so we're taking the size of that here. Now, where did these numbers come from? Let me say that these are precisely these averages in this Q goes to infinity limit in the function field case. So we didn't come up with these numbers. The function field world gave us these numbers as, this is the truth from my work with Yuan Liu and David Zurich-Brown. These averages in the function field case are precisely these numbers for each B. And so these numbers are easier to state than the distribution itself. So, of course, what's really new in our conjecture is that we're combining it with this fact that we can actually know that there is a unique distribution with these moments, and moreover, to say what it is. Yes.
You're wondering about discriminant.
In the function field case, you should take the radical of the discriminant, or it's like the product of ramified primes, actually. In the function, yes. And so, yeah, I would say, making a conjecture, I would say, yes, you should take the product of ramified primes. That's in order to have a conjecture, we should state something specific like that. But I think that there is still some interesting questions to think about with that average. And there's some recent work of Koymans and Pagano that questions whether the product of ramified primes is even right, even though it helps in a lot of cases. But so part of what we do is to give explicit formulas for this distribution. Now, the formulas for the distribution itself are more complicated than the averages. So I'm going to give them in one case to give you the flavor of them and also to see the kind of interesting feature that pops out. Okay, so I'm going to give you in one example. So this is G equals C7, the cyclic group of order 7. So this is for cyclic degree 7 extensions, say just even of the rational numbers. So let's let Q be the base field. And we're going to look at P equals 2, so the CELO 2 subgroups of class groups of degree 7 extensions. So there are two non-trivial representations of C7 over F2. And an abelian 2 group with a G action has a rank for each of these. So basically, it's the number of copies of each so A mod 2A is some F2 is some representation of G over F2, and so it has some number, it has no invariance, so it has some number of copies of one of the non-trivial representations and some number of copies of the other. So we'll call those ranks A1 and A2. And so, for example, if A is a abelian 2 group C7 module with ranks A1 and A2, we conjecture that the probability that the class group has CELO 2 subgroup isomorphic to A as a G module is the following expression. And before we parse this expression, I just want to make sure it's clear, where did this expression come from? So, okay, I'll just go back. On the last slide, we have these moments that come from a function field theorem. The function field theorem proves these averages. And then my work with Sawin our work on the moment problem gives a method via which one takes these averages and puts them through a machine that we've built to work backwards and find what the, it outputs what the distribution must have been to give you these moments. So this expression, we came to from looking at the function field moments, averages, and then the work to explicitly give what distribution would give these averages. So when you first look at it, a lot of features are similar to some of these formulas we've seen before. A bunch of products like this. You see this nice size of the automorphism group of A as a G module that you expect in the denominator. And we've got a factor that involves the two ranks, the ranks for the two irreducible representations. But then over here, you have some factors for some different cases, and one of those factors is 0. So if you have a CELO 2 subgroup with a C7 action who has sort of the number of copies of one of the irreducible representations of C7 is like one more than the number of copies of the other, our conjecture says that we think that happens 0% of the time. And so for general G, the formulas are essentially quite similar to this. They involve all the non-trivial irreducible representations of G mod P, and the exact precision of the formula depends on those. But that gives you a sense of the sort of cosmetic shape of the formulas. However, in the formulas, the behavior of dual representations is not independent. So here, you see that in this A1, A2 exponent here, but then you also see it really dramatically in this 0 over here. And some G modules are predicted to occur with probability 0. So these last two features, the feature that in our conjecture that the behavior of dual representations are not independent and that we predict some G modules occur with probability 0 is unlike all previous conjectures of Cohen-Lenstra-Martinet, Malle. All of the previous conjectures had conjectured that everything happens a positive proportion of the time. Though I do want to say that it was noticed by Ben Breenan, Ela Varma, and John Voigt especially in this case and similar cases of cyclic abelian groups, that there was something wrong here, and that probably not, that there were some restrictions on the behavior of class groups, and
So
yeah.
happening 0% of the time, but still infinitely often.
Well, that's a good question. So then you wonder. So from the function field theorem, and then I guess these probabilities in a Q goes to infinity limit, appropriately with all the limits written in, are also then a function field theorem, and that just says 0% of the time. And so Peter asks exactly the right next question, which is like, okay, so does it happen just infrequently, or does it never happen? So it sort of takes you a step backwards to the question of like which modules can occur. So the philosophy of Cohen-Lenstra-Martinet was, okay, what do we know? We know it has to have a G action, invariant free. Now that we know everything we know about it, we just conjecture it's one, sort of 1 over odd after that. But in fact, it turns out that there's more to say about which modules can ever occur. So if we take some prime, you could ask, what ZPG modules can occur as the CLP subgroup of the class group? So I took the group ring here, and then I quotiented out by the sum of all the elements to get rid of the invariant part. So which invariant-free abelian P groups with a G action can even be the CLP subgroup of this reduced class group where we got rid of the fixed part? Okay, so I wanted to introduce the notion of a P to the L rank of a group. So if you take the P to the L torsion, mod the P to the L minus 1 torsion, that's a FP vector space. It has some dimension, and that's what I'm going to call the P to the L rank. So of course, if you just care about your P group as an abelian group, you just need to know the P rank, the P squared rank, et cetera. And so what we actually show is that if you have a finite group and a prime not dividing the order of the group, and some base field K0 that has U complex conjugations and contains the P to the rth roots of unity, if you take a Galois G extension, for every pair of distinct dual irreducible representations of G over FP, and now I need some invariance to state everything of those, so of dimension Dn, so I'm calling Dn the dimension, and I'm taking the idempotents in the group ring that pick out the parts of the G module corresponding to those representations, and D is the degree of the splitting field of the representation, so that's why I called the representation dimension Dn, because it's a multiple of D, the degree of the splitting field. There is actually, this is not a probabilistic theorem. This is a theorem in the number field case. Of course, also the analog is true in the function field case, about the difference of the P to the L ranks of the parts of the class group corresponding to dual representations. And so it says they can't be too far off. So I wrote the upper bound over here. I wrote this factor of Dn because that's the dimension of the representation. So the P to the L ranks are all multiples of Dn. So if you wanted to just say, well, how many copies of the representation do you have, you would divide out by the Dn. And it's bounded by U and N. So that has to do with the dimension of the underlying representation over the algebraic closure, and the U, how many complex, or how many places, how many infinite places, I said complex embeddings, yeah, infinite places the field K has. And so we saw, over Q that, and in some case that the ranks differed by at most 1, so that was a case where U and N was 1, or not the ranks, but the number of copies of the representation differed by at most 1. All right, so, yes? Yeah, so so this is only on on dual representations and not on anything else. I want to mention that, so special cases of this follow from work of Leopold and Gra that were quite a while ago, but I think no one was quite looking at them in this setting. And I also want to point out that if over function fields, if you allow Q to vary, that this result is as strong as possible. So this result exactly covers all the cases that we predict happen with probability 0. So this did not have to happen a priori, but it's a phenomena that seems to happen in a lot of these similar analogous questions that, in fact, the things that happen with probability 0 never occur. So this precisely, in our conjectures about the distribution of class groups, any time that we conjecture some CLP subgroup G module structure occurs with probability 0, that is actually a theorem. It follows from this. So this precisely proves all the zeros in our conjecture, and sort of conversely, anything that satisfies these inequalities on the ranks between dual representations, at least over function fields, is possible, again, from this probabilistic theorem that came from finding the moments, proving certain formulas that the distribution has, and then observing that in many cases those formulas are positive, and so you have some case of that. And so the thing that really, you can look at the moments and look at these averages. The average number of surjections to every group is positive. And so really the new thing that happened here that I think is quite interesting is that when you use our work to find the distribution from those moments, you get those explicit formulas, and sometimes zeros appear. And then when those zeros appear, they beg you to understand why. And in fact, this is not a very difficult theorem to prove. As I said, some special cases were known. Why did Leopold and Gra not have the whole theorem? I mean, maybe they didn't know, maybe they didn't care about this question particularly, but maybe they didn't know where to look. And one nice thing about getting these explicit distributions in the function field case, where sometimes you have positive probability and sometimes you have zero probability, is now you know exactly where you're looking, exactly what restriction you're trying to prove. When you know where to look, it's not so hard to show this.
If you're going to say a word about your inverse moment problem, which tells you the support of the measure, I mean, you know the support of the measure.
Well, I don't know that I'm going to say that much more about the inverse moment problem. It's a good, I would love to, but yeah, I didn't put that so much of that in this, in this talk. But that's, that of course is a big, that's a big piece of the machine behind this. But what I did want to explain in a little bit of my remaining time was what's happening? Where is this restriction coming from? Because it's really not so mysterious, again, once you know where to look and precisely what you're looking for. And it comes from a reflection principle. So probably if you have heard of reflection principle before about class groups, you've heard of the Schultz reflection principle, which says that for a fundamental discriminant, the 3 rank of the class group of a quadratic field Q adjoining the square root of D is pretty close to the 3 rank of its buddy class group of its buddy number field Q adjoining the square root of minus 3 D. Those 3 ranks differ by at most 1, so that's very classical Schultz reflection principle. And when you look at that first, from a very far distance, it's like, oh yeah, that's kind of like what you had on the last slide. You had some difference between some ranks and they were bounded. But then you take like one step closer and you're like, wait, but these are 2 different fields. And what we had on the last slide were class groups of the same field. But in fact, if we look at the biquadratic field, and sorry, that should be a comma there instead of a period. So that's a biquadratic field. You would join the square root of -3 in the discriminant. So that is a extension of the rationals with class group Z mod 2 cross Z mod 2. And the class groups of these quadratic fields are actually parts of the class group of the biquadratic field corresponding to two different irreducible representations of Z mod 2 cross Z mod 2. So from that point of view, this is about, instead, the class group of this biquadratic field. And it says, okay, in this biquadratic field, the part of the class group coming from this one irreducible representation from Z mod 2 cross Z mod 2 can't be too far off of the part of the class group coming from this other representation of Z mod 2 cross Z mod 2. So viewed from that light, it's a very similar kind of thing to what we said on the last slide. And so I think perhaps some of the difference in perspective is seeing these reflection principles as, as giving restrictions on the class group of a single field, as opposed to relations between the class groups of different fields, which of course they also can do that. But here we're taking this perspective of thinking about it as restrictions on the class group of a single field. And from my point of view, this reflection kind of principle, one way to think about it is that it comes from a pairing. So if we have some field K with p to the rth roots of unity, if I take the maximal unramified p to the r torsion extension of K, I can understand that extension in two ways. The first way is class field theory. Class field theory tells me the Galois group of such extension is precisely the class group mod p to the r. On the other hand, if I take the sort of virtual p to the rth powers of K, so I let S be the set of elements of K star whose valuations are all divisible by p to the r. This is close to the p to the r torsion in the class group. I can take the map where you take the p to the rth roots of ideal generated by an element, and that gives a map from these virtual p to the rth units to the p to the r torsion of the class group. And then I said there were two ways that we understand H, this maximal unramified p to the r torsion extension of K. The fact that we have p to the rth roots of unity means that we can also use Kummer theory to describe the p to the r torsion abelian extensions. And the fact that they're unramified means that they had to come, Kummer theory says, well, they had to come from taking the p to the rth roots of something, but they're unramified, so they had to take the p to the rth roots of things whose valuations were divisible everywhere by p to the r, so that they had a chance of being unramified. And so Kummer theory gives us a perfect pairing between this Galois group and some subgroup of these virtual p to the r powers. And so, but then on the one hand, we said that this class group, or this Galois group is the class group mod p to the r, and on the other hand, by Kummer theory, it pairs with something that's close to the p to the r torsion of the class group. And notice that I said close. So, that is related to this inequality. It's not that we actually get a pairing between the class group mod p to the r and the p to the r torsion, but we get a pairing between something that is off by some controlled amount. And that's why you see an inequality between the ranks of representation and its dual, and not an equality. And so that gives you some idea of one way to see where these restrictions are coming from. All right, and so I will just summarize. These are just things that I've mentioned before, but I just wanted to sort of leave you with the takeaway, which is, we started from a probabilistic function field theorem, and maybe you thought, well, I don't care about these statistical theorems, and I don't care about function fields. Well, if you don't, but that somehow took us to a theorem in the number field case that is simply about existence, non-existence. It's not even about distribution. So this is the result about, the restriction on what can be the G-module structure of a class group. As I said, because of the function field theorem, if you do care about the function field case, this non-existence theorem is as strong as possible. And when this inequality is satisfied in all the cases of G-module structures that satisfy this inequality, we give an explicit, and I didn't put it out on a slide, but it just looks like a version of the C7 case that you saw with more products and indices. We give explicit conjectures for some positive probability that we think you get class groups of G extensions with that structure, which we know holds in a Q goes to infinity limit in the function field case. All right, thank you.
For our speaker. I'd like to start out with a question that's just the Q goes to infinity limit in the function field case.
Yes.
So there are two ways that can occur. So one way is you take P as a fixed prime and you let its powers go to infinity. And the other way is where the prime goes to the infinity as the first power. Mm-hmm. Can you comment on that?
Yeah, that's a great question. And, well, there's actually a third way, which is you can not care. And you can let Q go to infinity. And so, yes, so it...
that's why I'm checking.
Yes, and so ours is the third way. So you can do either of those things, but you don't have to do either of them. So you can either, say, go through the primes and let your prime go off to infinity, or you can fix a prime. Well, the problem with fixing a prime is in this, since this has to do with how many roots of unity you have, you want to fix the GCD of sort of the group that you're asking about and Q to the R minus 1. So you probably, because you're doing that, you can't actually go through a single power of Q. But as long as Q goes through prime powers to infinity in some way where you fix the relevant number of roots of unity, then you get, you get this. So.
It is remarkable.
Yes.
The reason I asked this inverse moment problem in some of your non-abelian theories,
yeah.
That's a very delicate business. Is it less delicate here? I mean, the inverse moment problem here, the space on which you'll be distributing is much simpler. So sometimes these are very subtle things, even classically, to reconstruct a measure from the moment.
Yes, yes. So I would say it is not it is certainly not as delicate in the non-abelian case, but it is. It takes some. There are many pages of calculations, but so it doesn't. It takes some work, but it is certainly much more delicate in the non-abelian group case. Yes, Evan?
I'm curious, what does the analog of this theorem look like in the function field case, and in particular, what happens to this parameter u? My experience with Schultz-type reflection theorems is that they tend to get tighter in the function field case.
Yeah, so our result in the function field case, that's a good, to be more clear, the result in the function field case is only over a K naught that is a rational function field where, so I misspoke in the generality that I said before. It is only in the case, only over the rational function field where you fix one place at infinity, as it is currently in the literature. I mean, I think, yeah. Yeah, so here in the analogy, in the function field case, you sort of pick one place to be an infinity, and then what do you mean by the class group? You mean the sort of class group of the ring that the rest of the curve, when you throw away the point at infinity, is spec of that ring. Yeah.
So in general, you expect U to be something like the genus or tonality of the function field?
No, U is always like the number of points that you set to sort of be infinite places, which means that from the function field point of view, if you're taking something like your Picard group, you're then taking the quotient by those places.
Because otherwise you've got the degree map. The Picard group is not behaving.
Right, yeah. So in the function field cases, you get to sort of pick arbitrarily as the number of places that you decided to be infinite places, and what that affects is what you actually call the class group. You know, then you pick whatever you want to call the infinite places, and then what you call the class group is the class group of the ring that that spec of it gives you the affine curve without those places that you declared to be infinite. Yeah. Yes?
You said that heuristically, each class group should carry 1 over the probability, the homomorphism.
Yes.
Then you said not true, but you said then you have some extra structure, extra pairing. So is it true now when you have this extra structure?
Yes, so that's a great question, which is, okay, there's some kind of pairing structure, and is, now, do you expect sort of 1 over the number of automorphisms with that structure? So in all of these cases, it was never the case that everything was just 1 over the number of automorphisms, because there were already these factors coming from the infinite places. And so in these formulas, it is still not the case that the formulas are 1 over odd of this with the structure coming from the pairing, because there is, in fact, a little more structure that is behind this than what I just presented here. And so this is not in this paper, but in our forthcoming work about a non-abelian analog of this problem, we consider the further structure, which is a class in the third homology group with the coefficients in however many roots of unity you have, that gives these pairings, and is, we think, kind of all of the structure that you need to see. But that is not yet in the paper that you can read online, but will be forthcoming in a more general paper that understands Galois groups of maximal unramified, not necessarily abelian extensions. Yes? Yeah, so can you do something where you throw away some number of primes? Yeah, so yes, you could ask if you don't want to go to such high degree number fields, but you want to investigate the situation where, like, U is supposed to be bigger, you could also do this where you could declare in the number field situation that some of your primes are now infinite, pseudo-infinite, and you could take the class group mod those, and then you would expect to have analogs here where you've added those infinite places. Yeah, so that is certainly something to be considered, and if you wanted to check this numerically or via tables, that would probably be a good way to check the higher U kind of cases.